For us, life unfolds on human scales. Miles, feet, inches. But beneath the surface of things is another realm, 1 billion times smaller than we are. A dimension that holds the secrets to understanding our world. What makes steel strong? Why ice cream is delicious? What makes life possible? Secrets that help us create what we imagine.
The human creativity of chemistry, there's just nothing more beautiful than them.
This is the realm of chemistry, and these are its greatest discoveries. Ancient Greek philosophers believed there were just 4 elements: earth, air, fire, and water, and that air was the underlying element, a single substance responsible for the makeup of everything in the world. Centuries later, Leonardo da Vinci was among the first to suggest that instead of being an element, air might consist of 2 different gases. It remained a mystery until our first great discovery. England, the latter part of the 18th century. Clergyman and sometimes scientist Joseph Priestley conducted a series of experiments searching for new airs, what today we call gases.
So the thing about the 18th century...
To find out more about what Priestley was up to, I paid a visit to Arnold Thackeray, president and historian at the Chemical Heritage Foundation in Philadelphia, Pennsylvania.
Doing this, and Priestley wrote and wrote and wrote on every subject that you've ever thought of. He wrote about history, he wrote about religion, he wrote about politics, he wrote about science endlessly. And Priestley was the man who knew everything. He would tell you the practice of it, the history of it, the theory of it, and he was quite literally the man who knew everything.
But along with everything else, Priestley did this famous experiment, right?
That's exactly correct. And there are 2 things that go into that experiment. The one is mercury, this strange substance that's simultaneously a liquid and metal. And that's just crazy. I mean, whoever heard of a liquid metal? And so it was really puzzling. What is this thing? And people were fascinated by it, and so they wanted to explore it. And of course, the other thing that went into it was the technology to deal with gases. And here in Priestley's experiments and observations on different kinds of air, we have the technology of collecting gases over liquids.
In tubes that you could see through.
Exactly. So you can see the gas, you can see what's happening to the gas, and now you really are in business. What Priestley does is he takes a burning glass to give him heat, a lens. He focuses it on this orange powder, the mercuric calx. He heats it, it changes into this metal mercury, and a gas comes off. But Priestley doesn't really realize what it is that he's found.
The answer would emerge in 1774, after Priestley paid a visit to Paris and shared the story of his discovery with another scientist, Antoine Lavoisier.
Paris is a marvelous place for Priestley to visit because Antoine Lavoisier is in Paris, talk of the town, doing the work that will end up as his elementary text on chemistry. And Lavoisier who is also mucking about with gases, hears what Priestley's done, is fascinated by the report of this new air, decides he'll repeat the experiment. He has lots of apparatus, better apparatus. He's a meticulous experimenter, and among other things, he weighs things. Lavoisier, by weighing, says something is being emitted. He calls the thing emitted oxygen. He rewrites the whole script of chemistry, and he creates a list of elements that we still use today: oxygen, hydrogen, sulfur. You can correctly say that Priestley discovered oxygen, but Lavoisier invented it. So with Priestley's experimental work on gases, with the discovery of oxygen, with Lavoisier's articulation of a system of language, we have the whole conceptual scheme in which 19th century academic work is built, 20th century industrial innovation. We have pharmaceuticals, we have biotechnology, we have cell phones, we have plastics, that's exactly right. And all these things begin with the discovery of oxygen. That's where it starts.
That's a lot to breathe in. In the early 19th century, a British schoolteacher named John Dalton was hard at work, pursuing his fascination with chemistry, which would lead to our next great discovery. Dalton's experiments showed that the known elements such as oxygen, hydrogen, and carbon combined in definite and constant proportions. From his calculations, he hypothesized that the elements must be made up of smaller, invisible pieces of matter with relative and distinctive weights. He called these pieces of matter atoms. So, what did Dalton discover?
Dalton's great discovery was what he called the relative weights of ultimate particles.
Ultimate particles.
That's what he called it. It's a lovely phrase. Later on, when he went public, it becomes atomic weights, and we know it as atomic weights, but it was ultimate particles.
So he used the word atoms.
He used the word atoms. The idea of an atom, of course, goes back to Democritus. The problem is, it's an idea. Is it any use? And Dalton was the man who made the idea useful. That was his great contribution.
From his work, Dalton developed what came to be known as his atomic theory, a revolutionary new system that defined the relationship between atoms and the elements.
And it's an enormously simple system, and Dalton thinks very simply, very visually. Here are the elements, here are the weight of the elements, here are the complex molecules. And it's a wonderfully effective system. It connects the thing that chemists can do, weigh things in balances, with the things that you can't see, the ultimate world of atoms. That's genius.
How important was Dalton's discovery? His atomic theory helped generations of scientists further unravel the mysteries of the atomic and molecular world, including our next great discovery. In the early 1800s, French chemist Joseph Gay-Lussac was conducting a series of experiments designed to study Dalton's atomic theory when he observed something odd. When he combined equal volumes of different gases and measured their reactions, the gases often produced twice the volume than he expected. How was this possible? The answer was provided in 1811 by Amedeo Avogadro, a physics professor at the University of Turin in Italy. While studying the results of Gay-Lussac's research, Avogadro had an insight. At the time, it was believed that gases were made of single atoms. Avogadro realized this assumption was wrong. The gases were made of multiple atoms, what came to be known as molecules. The realization that atoms could be rearranged to form molecules was the breakthrough that enabled scientists to move out of the chemistry dark ages and begin systematically creating new compounds.